Okay, so now we learned that we can electrically detect the magnetization or magnetic field. So next, let's think about how to manipulate the magnetization by electrical means. Okay, so in the classical approach, you can manipulate the magnetization by electrical means using this Ampere's law. So if you put the conducting non-magnet and apply the current in these directions, you can obtain the magnetic field due to the Ampere's law, so you can manipulate the magnetization. But actually, for applications, this is not an efficient way, particularly for the case that the size of the magnet is shrinked. So for the stable but small magnet, this way is not efficient. So people tried to think about an efficient way to switch the magnetization directions by electrical means, not relying on this classical approach. And so far, several approaches have been demonstrated. And one is spin transfer torque, and the other is spin orbit torque, and the electric field effect of VCMA is also a very attractive, interesting approach to manipulate the magnetization. Okay, so let me explain these three schemes one by one. So firstly, let me discuss what is the spin transfer torque. Okay, so firstly, let me start from a very intuitive picture of the spin transfer torque. So the spin transfer torque is torque exerted through the spin angular momentum of the conduction electron is transferred to the local magnetization. So this is the conduction electrons having spins, and this is the local magnetization. Okay, so when you apply the current, these spin can be interacted with the local magnetization, and as a result, the spin angular momentum is transferred to the local magnetization, and you can switch your magnetization. So this is the intuitive picture of the spin transfer torque. So let's elaborate so how to formulate the spin transfer torque. So let me firstly discuss the direction of the spin transfer torque. So this is the magnetic Tommel junction having two magnetic layers, and assumption is that this reference layer is very stable, so the magnetization direction doesn't change. But this magnetic layer, free layer, has the magnetization whose direction can be changed. And you now apply the current from right to left, then the electron travels from left to right. And before entering this reference layer, the spin direction is random, but once the spin electron enters this reference layer, due to the SD exchange interactions, the spin follows the magnetization direction of the reference layer. So the spin direction becomes uniform in this layer. And this spin enters this free layer. And then, because the magnetization direction of the free layer is different from the reference layer, so this electron has to change the direction of the spin. Then, due to the change in the direction of the angular momentum of the spin, the change should be transferred to the local magnetization due to the conservation of the angular momentum. So this is the fundamental principle of the spin transfer torque. So the SD exchange interaction and the conservation of the angular momentum are the two key mechanisms to explain the spin transfer torque. So the direction should be, the magnitude should be proportional to the relative angle between the reference layer and the free layer. So it should be described by M cross M reference. So the relative angle between M and M ref can explain the magnitude of describe the magnitude of the spin transfer torque. So the change in the spin direction, so the in the opposite direction, the spin transfer torque is exerted. And the direction should be this way. So that so if the spin, because the spin of the traveling electron changes from this direction to this direction. So the spin transfer torque should be exerted in this direction. So the opposite direction to the direction that the traveling electron spin is changed. So this is the direction of the spin transfer torque. And as for the magnitude of the spin transfer torque, this can be derived by considering the conservation of the angular momentum. So we should look at the change in the angular momentum for the conduction electron and the magnetization. And so this is the change in the angular momentum for the conduction electron, and this is the change for the change in the angular momentum for the magnetization. So due to the conservation of the angular momentum, these two should be equal. So from these equations, the delta m over delta t, so the change in the magnetization directions in the unit time can be derived like this from these equations. So we can introduce, we can add this term to the LLG equation here, so that this is the form of the LLG equations, including the spin transfer torque term. So the direction can be described by this factor, and the magnitude can be described by this factor. And this is the numerical simulation results of the LLG equation with the spin transfer torque term. So the magnetization starting to this point, so we apply the current spin transfer torque in, so that we inject the spin in the opposite direction. Then after the precessional motion, the magnetization switching can be observed in these configurations. So this is the time evolution of the magnetization along the z directions. So below a critical current that magnetized, so this is the initial value of the magnetization. So below a critical current, the magnetization is returned to the original directions, but above a critical current, it can be go to the negative directions. And if you increase the current to around several amps of the microamps, you can switch your magnetization within a reasonable time scale, less than a few nanoseconds. By the way, so this calculation is done for a typical value of the magnetic tonic junction. So you can switch your magnetization in current with the magnitude of somewhere around several tenths of microamps. Okay, and so so these are the pioneering works for the spin transfer torque. So as I mentioned, John Slonczewski and Luc Berger predicted the spin transfer torque in the magnetic multilayer systems. And in 1998, probably, the French group found excitation of the magnetic multilayers by injecting the electric current, and Cornell group showed the electrical switching of the magnetic domains by injecting the current in these multilayer structures. And so this work shows the full switching of the GMR structures. So these are the very famous works for the spin transfer torque-induced magnetization switching. And okay, so in addition, the spin transfer torque, in addition to the magnetization switching, the spin transfer torque can also give rise to several other phenomena. And one interesting phenomenon is oscillations. So this is the review paper of the spin transfer torque. So at the low current, as I mentioned, so if the current is small enough, the magnetization is settled down to the original north pole direction. But if the current is large enough, you can induce the magnetization switching like this. And in the regime in between these two cases, you can achieve the continuous oscillations. And this continuous oscillations was demonstrated experimentally in 2003. So by using these MTJ structures, they observed the continuous oscillations by injecting the DC current. So this spin torque oscillations can be understood by phenomenologically that so injecting DC current can be converted to the oscillating RF voltage, or because the magnetization oscillates by injecting the DC current, the RF field can be emitted. So this can be also used, in principle useful for the wireless communication, so the generation of the RF field. So this is a possible application of the spin torque oscillators. And then there should be an inverse process. And indeed, the inverse process was also reported by the Japanese team, Osaka University team, in 2005. So they use these magnetic tunnel junctions and they inject the RF current. Then, so because the DC current can generate the RF voltage, so in this work, the RF current generates the DC current. So this is the inverse process of the spin torque oscillations, and they indeed observe the rectified DC voltage by injecting the RF current. And so this is just an advertisement, but this was the work done by Hyunsu's team as a collaboration with Hyunsu's team. So we demonstrated the rectification. So that using the rectifications, the RF field can be converted to the DC voltage. And this is in principle useful for energy harvesting because there are the wireless signal around here. So the wireless signal means that the wireless signal is the oscillation of the magnetic field. So the magnetization can oscillate with the oscillating magnetic field. Then the low DC voltage can be generated by the oscillation of the magnetization. So this is useful, in principle useful for the energy harvesting. And indeed, in these papers, we reported the proof of concept demonstration of the energy harvesting using the 2.4 gigahertz wireless signal. So this is one of the interesting applications of the spin transfer torque. Okay.
What's the order of magnitude of the signal in the air?
I see. So the magnitude of the generated voltage, very, very good question. And so in reality, now it's very low. So please correct if I am wrong. So the magnitude of the wireless signal in this experiment is very, very, very high compared with the electromagnetic wave for our wireless communications. So, but in this experiment, the number of the MTJ is 8, so just 8. But we can integrate the million MTJs. Then we hope that it may be useful to generate a sizable voltage, even though a very, very weak wireless signal.
And which kind of MTJ do you use? Like
the
size of the MTJ that you use? Which diameter?
Material is cobalt iron bore MgO, and the size. So actually there's one key point. So the size. Okay. So it's elliptic shape, and the size was several tens of nanometer and around 100 several tens of nanometer. And one more key point is that we tuned the anisotropy so that it shows the resonance with respect to the 2.4 gigahertz wireless signal. So there was some tuning of the MTJ. Yeah, very good questions. Okay, so one more thing. So the spin transfer torque can also induce the magnetic domain wall motion. So let me show you the intuitive picture for the magnetic domain wall motion. So here we have the magnetic wire having 3 magnetic domains. So 2 is pointing this direction, and 1 is pointing this direction. And we apply the current in these directions. Then, so due to this SD exchange coupling, when the electron is in this domain, the electron's magnetic moment, spin moment should point these directions. And when the electron enters these domains, the spin direction should change with respect to follow this magnetization. And when this spin enters this domain, again, the direction of the spin should be changed to this direction. So, at this point and this point, the spin direction is changed. So, due to the conservation of the angular momentum, that change in the spin angular momentum should be transferred to the local magnetization. So, and as a result, we should be able to observe the magnetic domain wall motion by the spin transfer torque. And indeed, this spin transfer torque driven domain wall motion was observed in 2004 in nickel iron and dimanganese arsenide. So this is also another phenomena induced by the spin transfer torque. Okay, so next, spin orbit torque. Okay, so before describing what is a spin orbit torque, I need to tell you briefly what is a spin orbit interaction. Okay, the essence of the spin orbit interaction is that because it is the relativistic phenomena, so we need to think about the essence of the relativistic phenomena is that the phenomena should be the same regardless of what coordinate you consider. So imagine that this is the sun and this is the earth. Okay, so if we see these systems that the sun, the position is fixed and earth is rotating around about the sun. So this is the first way of the coordinate systems. And the other way is that sun is rotating around the earth. Okay? And these two should result in the same results. So these are the essence of the relativistic phenomena, relativistic theory. Okay, then for the left picture, the Earth or the electron should feel the electric field by the sun or the nucleus. Okay, so the electric field that the electron feels can be described by this Gauss's law, okay, Gauss's principle. And on the other hand, for the right case, because the plus charge is rotating around the electrons, so this means that the magnetic field, so the electron feels the magnetic field, and that can be derived by the Biot-Savart's equation. So the Earth feels the magnetic field. So due to the guideline of the relativistic theories, this E and this B should link with each other. Okay, and that's the point. So by connecting these two equations, this magnetic field can be described by the electric field. So this is the very important point. So this magnetic field is can be described by this electric field. So the point is that the electron moving in the electric field should feel the effective magnetic field. Okay? So this is the important point of the spin-orbit interactions. And this is a very classical picture, but if you consider the quantum mechanics, one correction factor 2 is added in this denominators, but this is not so important. So the point is that these two are the same. So the electron moving in the electric field should feel the electric, so effective magnetic field. So this is a very important point. And this, by introducing this concept, this anomalous Hall effect and the spin Hall effect can be understood. Okay, so let me explain. So the intuitive picture of the anomalous Hall effect and the spin Hall effect. Okay, so now the electron travels in this z direction, and here is the atomic nucleus. Okay, so the if you change the coordinate, this is equivalent to this cases in which the atomic nucleus approaching to the electron. Okay, so these two should be the same. Okay, then so let's think. So in this case, the nucleus forms the electrostatic potential with gradient. Okay, and in this case, the nucleus forms a magnetic field because this is a current. So the current should generate the magnetic field with gradient. Okay, so if your electron has the spin in this direction, and the nucleus, so this is your spin, and if the nucleus pass this way, then the magnetic field is generated this direction. Okay, so the spin, so if the nucleus pass this way, the magnetic field can be, so the direction is opposite. So it moves to this direction because this is more, so the going this way should result in the less magnetic field, whose direction is opposite to the original spin. And if the current pass this way, then the magnetic field direction is the same with the spin. So going to this way should result in a larger magnetic field with the same direction. So the this up spin should move to this direction. And if the spin has this direction, then if the nucleus pass this side, then the spin should move to this direction. And same is true for the case that the nucleus moves this direction. Then again, the spin should shift to this direction. So in short, by using this coordinate, you can understand that depending on the spin directions, the transverse motion is induced, and the direction of the motion depends on the spin. So the up spin goes to this direction, and the down spin goes to this direction. So the spin current is generated by considering this systems. So this is the essence of the anomalous Hall effect and the spin Hall effect. So you can obtain the spin accumulation in both sides of the systems. And because the ferromagnetic systems has the unbalanced number of the electrons, so you can obtain the finite voltage for the anomalous Hall effect, but you do not obtain the finite voltage for the spin Hall system because the spin polarization factor is 0 for the non-magnetic systems. So this is a very intuitive understanding of the anomalous Hall effect and spin Hall effect. And we can define the magnitude of the spin Hall effect by introducing the spin Hall angle. So it can be expressed by the ratio between the spin current and the charge current by this way. So if the spin current is large, the spin Hall angle becomes large. So this is the definition to represent the magnitude of the spin Hall effect. Okay, and the first observation of the spin Hall effect was reported in 2004 and 2005, and because it cannot be detected electrically, the first observation was achieved by using the optical method. So they use, so in this case, they use the Moog microscope to observe the spin accumulation in both sides of the wires. And so this is also similar. And so this work also uses the optical way to detect the spin accumulation in both sides of the wire. Okay, and regarding the magnitude of the spin Hall effect, it was around 10 to the minus 3 to 10 to the minus 4, so it was very small at this stage. But so next, let me discuss the inverse process of the spin Hall effect. So this shows the pattern for the direct spin Hall effect or the simply spin Hall effect. And this is the inverse process of the spin Hall effect, so inverse spin Hall effect. So so in this system, the up spin goes to right and the down spin goes to left. So if we can induce the spin current by some means, then so the spin current flows in this direction. Then the down spin goes to left, and the up spin goes to right. This means that the charge is accumulated in both this side. So we can obtain the finite voltage using the inverse spin Hall effect. So this requires the spin current. So if you can induce the spin current by some means, you can obtain the finite voltage to detect the spin current. And using this inverse spin Hall effect, so in 2006 and 2006, the researchers in Spain and Japan observed the spin Hall effect, so the inverse spin Hall effect in aluminum and platinum. And one surprising thing is that the magnitude of the platinum, or the spin Hall effect for the platinum, is 10 to the minus 2. So it's much larger than the previous work in which the 10 to the minus 3 to minus 4 spin Hall number was reported. Okay, so so these are the spin Hall effect. Okay, and next let me explain what is the Rashba effect, which is another important phenomenon of the spin orbit giving rise to the spin orbit torque. Okay, so the Rashba effect is similar to the spin Hall effect, but so this is the cartoon to explain the Rashba effect. So you apply the current in this direction, and there's an electric field in this direction. Okay, so and because as I mentioned, the traveling electron in the in the electric field should feel the effective magnetic field. So that's the essence of the spin orbit interactions. So the traveling electron having the momentum of P should feel the magnetic field. And this effective magnetic field is called the Rashba field. Okay, and this is the Hamiltonian of the Rashba effect. So it is proportional to the K wave number, and this is so alpha R is the Rashba constant. Okay, so if we consider the Rashba effect, the Hamiltonian of the electron traveling in these systems can be described this way. So the first term is the kinetic energy. And the second term is the Rashba energy. Okay, so if without this Rashba term, as you know, in the continuous space, this density of state can be described by simple parabolic relations. But because we have this Rashba interactions, and this sign depends on the sign of the spin, so the up spin, so this spin shifts to this direction, and the down spin shifts to this direction. And this is different from the Zeeman splitting, in which by applying the magnetic field, this spin energy becomes go up, and the down spins becomes go down. So the Zeeman splitting and Rashba splitting are different in this way. Then, so looking at the conduction electrons in these systems, then for the Zeeman splitting case, all the electrons traveling in all the directions has the same spin polarizations. So for any directions, this down spin, population of the down spin should be larger than the number of the up spin. But for the case of the Rashba splitting, the electron traveling in this direction, plus k direction, has a larger number of the up spin than the down spin. But the electrons traveling in the minus direction should have a larger number of the down spin than the up spin. So the spin polarized current is obtained, and the spin polarization direction changes with the applied current. Okay, so that's the point. Okay, and also so the moving electrons are spin polarized, and the polarization direction depends on the sign, direction of the magnetization. Okay.
So, Professor, here, because it's, the way I'm thinking is that the graph has been shifted, translated towards the right, because of the term alpha r k sigma, right?
Mm-hmm.
But why isn't the minimum at zero energy? Because it's like h.
This is probably a junior high school mathematics, but this.
No, I'm just saying that just for the kinetic energy, shouldn't it be crossing the zero at the minimum?
So this point. But if you introduce k equals 0, the energy becomes 0.
Yeah.
Mm. So mathematically, sorry, I did not catch the point.
I was just saying that shouldn't the parabola be crossing the 0 point at the minimum, at the global minimum?
Here?
Yes.
Okay.
Because the translation should only be shifted towards the right,
No.
not up or down, right?
No. Let's introduce k equals 0 to this equation.
Mm-hmm.
Then HR should become 0.
Yes.
So it means that this curve should cross origin.
That's what I'm saying. For k equals 0, E would be 0. Or, I mean, isn't H
Yes,
E here?
H?
Isn't H energy here? I might be wrong, I'm just
Yes.
curious.
Okay, so I think that we should discuss later. Okay, thank you. Okay. Okay, so the prediction of the Rashba effect was done by assuming this system, so the three-layer systems. But after that, Edelstein predicted the same effect in an interface. So in the interface, the effective field is already built in. So the electric field should be there at the interface. So the Edelstein predicted that at the interface, the Rashba effect is observed. So it is called, the Rashba effect at the interface is called the Rashba-Edelstein effect, or simply Edelstein effect. Okay, so the observation of the spin-orbit torque was firstly done in, again, the H. Saito's team in 2008. So they observed the effect of the spin-orbit torque by the change in the line width of the FMR. So they use platinum permalloy bilayer stacks and measure the FMR in these systems while injecting the DC current. Then, due to the spin-orbit torque generated by the platinum, because the spin-orbit torque is a damping-like torque, so the observed damping magnitude of damping changes with the spin hole, the injecting current. And indeed, the damping constant, observed effective damping constant linearly changes with the applied current. So this is the first observation of the effect of the spin-orbit torque. And then the magnetization switching are reported in these three papers. So the first observation was done using the gallium manganese arsenide by the team of the Purdue universities in probably 2009, yes. And then in the stacking systems, the spin-orbit torque switching was achieved by platinum cobalt and tantalum cobalt ion boron. And Chi-Feng is one of the authors of these papers. And okay, so this is my paper. So far, the spin-orbit torque-induced switching can be classified into these three schemes. Type Z, so we call type Z, type Y, and type X. So the spin-orbit torque can induce the magnetization switching for the perpendicular magnetization and in-plane magnetization. And the in-plane magnetization switching can be further classified into the type Y and type X. So the current is applied in the X directions, and then the spin-orbit torque can switch the magnetization along the Y direction and X directions. But these three are very different in a sense that the magnetic field is necessary to induce the magnetization switching for type Z and type X. So for the type Z, you need to apply the field along the X direction to induce the magnetization switching, and that is also the case for the